So today what we're going to do is we are going to talk about stoichiometry. Um, this follows in the Brown-Lemay text. It's going to be section 3.6 and 3.7. So starting things off, we are going to learn a lot about what's happening in a chemical reaction by looking at a balanced chemical equation. I want to emphasize a few things here. When you look here, you're going to see that 2H2 gas is combined with O2 to make 2H2O. Now, it isn't shown in the equation, but one oxygen is going to be present there. And by looking at that data, we can see that there are a number of different comparisons we can make on different scales. First off, on the molecular level, we could say that in its smallest, most simple form, 2 molecules of hydrogen react to 1 molecule of oxygen to make 2 molecules of water. But we don't typically work on that scale. So by using Avogadro's number, 2 times 6.2 times 10 to the 23rd, we find that 2 moles come from that coefficient of 2 as well, or 1 mole on the oxygen side, and again, 2 moles on the water. Now, a little bit more visually, we can see that same information presented right here. So the chemical equation is shown once again, 2H2, O2 making 2H2O. Visualizing that, we see these white spheres represent our hydrogen atoms. So 2 molecules of H2, those hydrogen atoms are bound together into 2 discrete molecules. Then we have our oxygen, and they combine to form that H2O with 2 hydrogen atoms bound to a single oxygen. All of this hopefully should just be reviewed and pretty straightforward. Now, on a mole level interpretation, not the individual molecules, but again, on the large scale, we are going to look at this and think, well, 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water, these can be converted to masses. We use the molar mass from the periodic table, and we find 4 grams of hydrogen approximately come from 2 moles. 32 grams of oxygen come from the 1 mole of oxygen. Now, in combining those, we find that 4 and 32 combine to make our 36 grams that we start with. And then in the end, you'll notice that we have 2 moles of water. That's 18 times 2 is 36. So we also have 36 grams in the end. So we're obeying the law of conservation of mass. So all of that just to get this idea that we have a ratio of 2 moles of hydrogen to 1 mole of oxygen to 2 moles of water. And if I want to do any comparison, I can do that very, very clearly and very, very easily just by making sure that I figured out the number of moles of each thing and looking at these numbers as a ratio. So let's do a practice problem. First, when 1.57 moles of oxygen reacts with hydrogen to form water, how many moles of hydrogen are consumed in our process? So I want to think about that. Key information, once again, is that I have 1.57 moles of oxygen, and I know these reacting ratios. So I'm going to go into this problem, and I'm going to think, well, how many moles of hydrogen are consumed? The comparison is oxygen and hydrogen. It's just the O2 and just the H2. So really, it's not relevant to me that I have that 2 moles of water. It's just the 2 moles of hydrogen to 1 mole of oxygen. Now, in setting the problem up, we would say 1.57 moles of oxygen is our starting point. We want to cancel out those moles of oxygen to find the number of moles of hydrogen. And in looking at our reacting ratio, it's 2 moles of hydrogen for every 1 mole of oxygen. Our units would then cancel. Moles of O2 and moles of O2 go away. And we can do the math on that. And we've got our 1.57 times 2 going to be 3.14. And that is, again, now moles of hydrogen in the end. Okay, so we can figure that out. We can put that together. Now, let's look at a different reaction and see if we can make similar conclusions. So this time around, we've got a different reacting ratio. Let's identify in the problem the key information. We want to find the mass CO2, so the goal is grams of carbon dioxide, that is produced when 1 gram of the C4H10 is burned. So that's our given. This is our beginning here, is that 1 gram of C4H10. So to think through this process, we're going to want to go from grams of our C4H10. And in order to do a comparison using these coefficients, I have to get into moles. So into moles of said C4H10. The next step in that process is to look at the ratio and convert from mole to mole. Now I want to go to moles of carbon dioxide. Finally, 2 grams of carbon dioxide. So as you break this down, you can do this in a number of ways. You can do them as individual steps, or you could combine them. I'm going to do these as individual steps to begin, just to hopefully clarify each point. So I'll begin here, grams of C4H10 to moles of C4H10. So are going to know in this problem is by finding molar mass, we get that it's 58 grams per mole, grams of C4H10 in order to convert to moles. So we're going to take our 1 gram of C4H10. We're going to convert that. Remember, grams per mole, it's 58 grams for every 1 mole. So our first step leads us to 172 times 10 to the negative 2 moles of that CH10. Okay? So step 1, check. We've gotten to this point now, moles C4H10, right there. The next step in the process is to take those moles of C4H10, and we want to use that as a starting point to convert into moles of CO2. So we do that in our next step to get rid of moles of C4H10 and to go into moles of CO2. We're going to look at the reacting ratio. So above, we can see CO2 has a coefficient of 8, C4H10 has a coefficient of 2. We use those in our fraction, 2 moles C4H10 to 8 moles CO2. In that process, we multiply at the top, divide by the bottom number there. We'll show our cross cancellation of units. What we end up with is 6.88 times 10 to the negative 2 moles of carbon dioxide. Okay? So now that I'm to this point, I'm almost there, right? We've got mole CO2, and that's mole CO2, right? So the final step is to go from moles back into grams, and that's my last stage right here. I'm going to take 6.88 times 10 to the negative 2 moles CO2. We're going to use the molar mass of carbon dioxide, which we have at 44 grams CO2 for every 1 mole CO2. And working that out, you get 0.03 grams of carbon dioxide. So that got us to our final step in the process, gram CO2, gram CO2. So we could alternatively combine these stages, and we could say, well, beginning with 1 gram of carbon dioxide, or sorry, not carbon dioxide, but the C4H10, I can set up a series of steps that accomplish the same thing. Put all of those individual steps together, the 1 mole C4H10 to 58 grams C4H10. Cancel out your 2 moles C4H10 for 8 moles CO2. And finally, the 1 mole of CO2 for 44 grams CO2. Works out exactly the same. You cancel out your units, and you find that you still end up in grams CO2 with that same final answer, 3.03 grams of carbon dioxide. Okay, so you can do this in multiple stages. Just know that it's going to take a little bit more time, and you might have a little bit of rounding error. I definitely prefer just combining these into a single chain of conversions. So next thing that I want you to consider is this. If 1 gram reacts with 3.59 grams of oxygen, so that's our C4H10, same exact scenario as last time, and it's going to make 3.03 grams of carbon dioxide, figure out the amount of water produced using only addition and subtraction. So take a second now and see if you can work that out. If you put it together, hopefully you get that 1 and 3.59 is 4.59 grams of reactants. Then on the opposite side, you had 3.03 of the CO2 plus some unknown number, but that unknown number has to be exactly the same as our number of reactants. So take your 4.59, subtract away your 3.03. Should end up with 1.56 grams of water being produced just by addition and subtraction. So you don't have to go through this full conversion setup a second time if you know enough information in the problem. Now, just to summarize that idea, if you have grams of some substance, use the molar mass to find moles of that beginning substance first. Once you've done that, use your coefficients in the balanced equation to go from moles of the first to moles of the other substance. Finally, to get back to grams, use your molar mass of that second substance. Now, we're going to work out our sample exercises. I'm going to try to break these down for you. You have these in the text reference also, very fleshed out, but hopefully this makes a little bit more to you as I break it up. So we want to know the number of grams of water produced. Okay, so that's my goal. We're going to focus on the water. In the oxidation of 1 gram of glucose, C6H12O6. So we have our glucose is the beginning, right? So we start here, and we're going to end with the water. We're trying to figure out how much of that is produced. So we're going to do our multi-step setup. We begin with our 1 gram of the glucose. And let's just predict our steps, right? We're going to go from grams of glucose into moles of glucose. So that will cancel out using molar mass. The second stage, we're going to try to cancel moles of glucose and convert that into moles of our water using the mole ratio. And the final setup is to cancel the moles of water and determine the grams of water by using molar mass. So we'll go ahead and put our numbers in for that. It's a relatively straightforward breakdown. Again, our molar mass, we're going to have 180 grams per mole on the glucose. Looking at our reacting ratio, we've got a 6 water to 1 glucose ratio, 6 to 1. So that's going to be a 1 on the bottom and a 6 up on top. And we have our water. 1 mole of water is going to be 18 grams. And we'll do that. I'll just leave it to 3 sig figs just to simplify the numbers a little bit for us, okay? So as we break this down, once again, it's 1 times 6 times 18, divide by 180, and divide 1, divide 1. With a 0.00 grams of water. So hopefully that was good. Go ahead and do the practice exercise on your own, and you can check your work there. Now we move on into sample 317. On the amount of reactants and products once again, but this time you're given this problem in more of a word form, so we're going to have to break this down. We begin with solid lithium hydroxide. It says we have 1 gram of this lithium hydroxide. They give us this wonderful key information that it's used to remove CO2 gas exhaled by astronauts, but, you know, for our problem, not super relevant. The goal is how many grams of CO2 could be absorbed by 1 gram of lithium hydroxide. So in this problem, what's going to be a little bit trickier is we're going to have to figure out a balanced equation first. We've got to think about lithium hydroxide. The way that formula comes together, we've got our lithium ion, the 1 plus, hydroxide ion is a 1 minus. So if I have solid lithium hydroxide, it'll be LiOH as a solid to begin with. Now, it says once again, it's going to form lithium carbonate and liquid water when it reacts with carbon dioxide. So we combine it with carbon dioxide, CO2S. It was going to make solid lithium carbonate. So we've got to remember, lithium was a 1 plus, but carbonate is CO3 2 minus. So that is going to be 2 lithium ions reacting with that carbonate to come together. And then our final piece was liquid water. So we've got that one as H2O. And we'll balance just to make sure that everything is good and consistent here. 2 lithiums on the right, need 2 lithiums on the left. We've got a single carbon, so that one checks out. We've got 4 oxygens on the left, and we've only got, and we have our 4 on the right. Okay. Now, not as relevant, but hey, they give us this. We're going to say it's liquid water, and they said that it's going to be solid carbonate. So we have our equation, and it's a 2 to 1 to 1 to 1 reacting ratio. Now we're going to do our gram to gram conversion in multi-step form. It's 1.00 grams of our lithium hydroxide. Now, as we plan out the conversions, remember we got to cancel grams of lithium hydroxide to find the moles of lithium hydroxide first. Then I want to cancel out moles of lithium hydroxide to change to the other substance. I want to know grams of carbon dioxide in the end, so I'll have to go to moles of CO2. The final step would be to cancel those moles of carbon dioxide to find grams of carbon dioxide. So we're going to put these together. We need to know that is 23.95 grams lithium hydroxide per mole. It's a 2 to 1 mole ratio of lithium hydroxide to carbon dioxide. And then our 1 mole of CO2 is 44 grams of carbon dioxide. So doing the math on this, it's the 1 times 1 times 1 times 44, multiplying all across the top, dividing 23.95, then dividing 2. When we do the math on that, you should get 0.919 grams of carbon dioxide as your final product. So double check that one, and then do the practice exercise for number 317. So that should hopefully wrap up this idea. We're going to get really, really comfortable with doing these conversions. And then I'm going to talk about limiting reactants next. But we'll do a quick pause and